Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we are looking at the emission spectrum of the hydrogen atom. So our question is, what is the nanometer wavelength of a photon emitted during a transition from Ni6 to the state of NF2 in the hydrogen atom? So all that's doing is looking at the principal quantum number of starting at 6 and then ending at 2. So it's dropping 4 levels. There's only one equation that we need to worry about, especially at this stage whenever they're asking about anything involving a wavelength and a hydrogen atom. Hydrogen atom specifically because at this state we're only given our constant, a rise constant for hydrogen. And that constant, that R constant, is R sub H to denote hydrogen, which is equal to 2.18 times 10 to the minus 18 joules. So that's really the majority of what we need in terms of constants. The only other constant, there will be one other constant that comes up in the second part, actually 2 other constants. So, but let's start with calculating the energy. We need to get to the wavelength, but we can't do that directly given the principal quantum numbers. So we simply need to get to energy first, because from energy, we could solve for wavelength, we could solve for frequency, we could solve for whatever we need. So our change in energy for the hydrogen atom, whenever it is emitting a photon, is R sub H times 1 over our initial quantum number squared minus 1 over our final quantum number squared. So plugging in our values, we can get R sub H, edit, so plugging in our values, we get 2.18 times 10 to the minus 18 joules times 1 over 6 squared minus 1 over 2 squared, which would be 1 over 36 minus 1 over 4. And all told, 136 minus 1/4 is negative 2/9. And that becomes very interesting once you've solved for this. Once you've done all the arithmetic out, you'll find that it's negative 4.84 times 10 to the minus 19 joules. Note this negative right here. That negative, you have to kind of analyze this equation just a tiny bit. We're looking at the change in energy. The change in energy is decreasing with that negative. And what that means is that this is an emission. That's all it's indicative of. The negative is telling us that this is an emission of energy, that this is energy that is leaving the system and going into the surroundings. So for our purposes, we do not retain the negative for the remainder of this problem in calculating the wavelength, because there is no negative wavelength. It wouldn't make any sense. But it's important to recognize what that negative means. When you're looking at thermochemistry, it would be called exothermic. If you're looking at Gibbs free energy, it would be exergonic. In this particular case, it just means that it is the emission of this electromagnetic radiation. So we have an equation for frequency. Frequency is simply equal to our speed of light constant divided by our wavelength. We have, or conversely, we have an equation for wavelength that is the speed of light constant divided by frequency. But first we need to figure out what frequency is. Well, frequency can also be listed as, because we're not given frequency in this problem, we can look at frequency as being delta E over our Planck constant. Because delta E is given in units of joules, Planck constant is given in units of joule seconds. So the joules cancel out and you're left with per seconds. Per seconds are the units of frequency. So you can kind of figure these things out if you look at the units, as long as you're not going rogue and trying to use formulas from other areas that have no relevance here. You should be consistently getting this correct as long as you follow the units. So lambda is going to equal, if you do the manipulation, it would be C over delta E over H, which that's basically saying speed of light constant times Planck's constant over our change in energy is going to give us our wavelength. So coming back to the other side here, we can list our two constants. We have speed of light, which is 3.00 times 10 to the 8th meters per second. We have Planck constant, which is 6.63 times 10 to the minus 34 joule seconds. And now we also have our E, our delta E, which we can work into this equation. Get a little more room here. Plugging in the values that we have for delta E, C, and H. So our wavelength will be 3.00 times 10 to the 8th meters per second times 6.63 times 10 to the minus 34 joule seconds, all over 4.84 times 10 to the minus 19 joules. So this is the wavelength of the light emitted, which is why the negative disappears. It's already taken into account of it because this is being emitted. Always remember that. So lambda, after you do the calculation out, will be 4.11 times 10 to the minus 7 meters. But we're asked to give it, if we come back up to the problem, we're asked to give this in nanometer wavelength. So we're just going to have to convert it over to nanometers, which is 1 times 10 to the ninth nanometers per every 1 meter, which gives us 411 nanometers. And that's our answer. So this was a little two-step problem. You have to recognize what constants are you given, what values are you given. You're given the principal quantum numbers only. You know that there has to be more to it, so you have to think in terms of constants. You know you have your R constant for hydrogen. That can be applied to this equation to get you energy. And from energy, you can solve using other constants to get you